Welcome to Module 12A of the Data Center Fire Protection Masterclass. This advanced training module focuses on smoke control, fire ventilation, and the interfaces with HVAC systems during a fire event. The central theme is how an engineered high-rise response coordinates conditions across multiple areas: the fire floor, adjacent zones, protected stairs, firefighter lifts, and basement parking. We'll also examine how HVAC systems transition into fire mode, so ventilation supports the overall smoke control strategy rather than working against it. Our learning path follows a clear sequence from identifying the fire zone to establishing the pressure objective, issuing commands, proving that those commands worked, and finally restoring the system safely. Along the way, we'll connect the operational controls, including pressure zones and the FFCP or FSCS, with the evidence required in the field. The key principle is that a smoke control system is not complete when it receives a command. It is complete when its performance is verified. We'll finish by considering reset and restoration, so the system can return to normal operation in a controlled and reliable way. This module focuses on the practical interface between smoke control, fire ventilation, and HVAC systems. The central objective is to translate a verified fire zone into stable airflow, tenable egress, and auditable proof. In other words, a fan showing on is not enough. We need to demonstrate that the system is actually delivering the required performance. We'll work through 5 connected activities: define the pressure and airflow objectives by zone, command the relevant systems, move air through fans and dampers, measure the results, and restore the system safely afterward. That means coordinating fire fans, dampers, VFDs, and life safety controls, while proving both operation and restoration. The intended audience includes fire, HVAC, controls, and electrical engineers, along with facility operations and commissioning teams. It also includes AHJ and fire service representatives, insurers, and emergency planners. By the end, the key deliverables are a zone and pressure control matrix, a cause and effect and firefighter control sequence, and a complete evidence pack covering calculations, testing, and restoration. Key interfaces include the FFCP, FSCS, fire and smoke dampers, differential pressure, and variable frequency drives. This module focuses on Section A, strategy, standards, and authority within a data center fire protection system. The central message is that equipment selection comes later. First, I need to define the conditions the system must support, the decisions it is allowed to make, and the evidence that will demonstrate successful performance. The framework on this slide is organized around 4 questions. What zone are we protecting? What is the objective for that zone? Who has the authority to issue commands or approve actions? And what evidence will confirm that the system meets the requirement? The learning path moves in a deliberate sequence from the fire scenario to the tenability objective, to the approved command, and finally to measured acceptance. That sequence helps prevent a common mistake: choosing devices or controls before the overall strategy is agreed and documented. As we move through Module 12A, the focus is on establishing clear pressure relationships, smoke zones, control hierarchy, and acceptance evidence. These elements create the foundation for a design that can be reviewed, authorized, tested, and ultimately accepted. This module focuses on smoke control, fire ventilation, and the interfaces with HVAC systems. The central point is that smoke control performance is measured in pressure and airflow, not simply by whether a fan is running. The system succeeds when smoke movement is controlled and doors remain usable under the approved operating combinations. The process moves from the fire zone to the control boundary to moving air, protecting egress, and finally proving performance. On the fire floor, exhaust helps control smoke movement, while makeup air must be low, distributed, and limited. The design must avoid disrupting the plume or creating uncontrolled inflow. In protected zones, including stairs, lobbies, and shafts, the approved positive pressure relationship must be maintained. Doors still need to open and close, and relief must prevent excessive pressure. Acceptance is therefore measured, not assumed. Fan operation alone is insufficient. We verify dampers, airflow, differential pressure, and door force, then repeat those checks in normal, standby, and failure modes. This is the practical connection between strategy, standards, and reliable life safety performance. A fan running is only a command state. It tells us that the system has been instructed to operate or that a control screen reports an active condition. It does not, by itself, prove that smoke control is working as intended. Command is not proof. The evidence has to come from measured performance. That includes the differential pressure across the protected space, the force required to open doors, and the airflow velocity or approved airflow through the system. These values matter because they describe what occupants and responders actually experience, not just what the equipment appears to be doing. The system succeeds when smoke movement is predictably controlled and doors remain usable under the approved combinations of operating conditions. That means evaluating approved pressure, adopted door force, and airflow together, rather than treating a green indicator as the final answer. In short, smoke control performance is demonstrated by pressure and airflow measurements, supported by acceptable door opening force, not by fan status alone. This slide establishes the central coordination rule for smoke control design. The smoke control zones must match the actual protected space boundary. That means mapping the fire floor and smoke zone together with adjacent floors, protected shafts, lift lobbies, transfer paths, penetrations, and MEP risers. These elements should be treated as one coordinated system, not as separate drawings. For the fire floor, identify the exhaust reservoir and pickup points, then locate makeup air away from the smoke layer. Account for doors, facade leakage, and service penetrations, and show sprinkler, fire alarm, and smoke control zones together. The egress and responder zones require equal attention. Confirm approved stair pressurization, include firefighter lift lobbies and shafts where applicable, and check door hardware, relief paths, and transfer openings. Responder access and communications must remain available. Finally, coordinate fire and smoke dampers, rated shafts, riser fire stopping, access doors, shared ducts, and any non-dedicated HVAC. Any architectural change or rack layout revision requires the smoke control boundaries and interfaces to be revalidated. This slide establishes the authority hierarchy for smoke control, fire ventilation, and HVAC interfaces. The key principle is that standards define the framework, but the approved analysis defines the project values. We begin with the adopted code and local basis, including the 2024 IFC Section 909 where applicable, Indonesian requirements such as Permen PUPR 26/PRT/M/2008 and SNI 03-6571-2001 where adopted, plus the approved fire strategy and any AHJ or damper conditions. Technical standards then provide the detailed criteria. NFPA 92 addresses smoke control analysis and acceptance. NFPA 90A covers air distribution and fire or smoke interface issues, and NFPA 72 addresses emergency control functions. NFPA 101 and 105, along with listed damper and fan requirements, complete that technical layer. Finally, the project evidence must support the design. That includes the zone matrix, calculations, door schedule, fan curves, leakage assumptions, control narrative, and FAT, SAT, and IST records. Calibration certificates, accepted deviations, and restoration authority also matter. Together, these sources create one defensible evidence chain, from governing requirements through witnessed field performance. The abbreviations at the bottom identify key controls and equipment, including the FFCP, FSCS, FSD, differential pressure, and VFD. This module defines the control sequence and governance for smoke control, fire ventilation, and HVAC interfaces. The central principle is automatic response starts the system, but firefighter control retains priority. The sequence begins with detection, followed by selection of the approved zone, an automatic command, manual override when authorized, and finally an approved reset. For automatic control, a verified fire input selects the required zone response. Commands are latched where necessary, and the fire alarm control panel chronology remains authoritative. Once firefighters take control through the FSCS or FFCP, the adopted manual priority applies. The last approved command governs, while indications must show the actual equipment state, not merely the requested state. Monitoring must prove downstream power, run or fault status, and equipment position. Pressure and airflow trends can support verification, but they do not replace field acceptance. Any mismatch or loss of supervision must be enunciated. Restoration is equally controlled. Reset is sequential and authorized, and normal HVAC must not restart into an unsafe zone. Before return to service, the system must be inspected, cleared, and documented under normal power, standby power, and component failure conditions. This slide presents the three-zone pressure concept used in smoke control and fire ventilation design. The key point is that this is a design strategy, not a universal preset. Where the approved analysis adopts it, the fire floor is maintained at a controlled negative pressure, adjacent floors are controlled positive, and protected shafts preserve the required egress relationship. On the fire floor, smoke exhaust begins only after the approved trigger. Makeup air is limited and distributed low, while pressure is carefully controlled, so it does not prevent doors from operating. On the floors above and below, supply or pressurization must follow the analysis, with particular attention to preventing smoke from being forced through shared risers. Actual leakage paths and door behavior need to be confirmed, not assumed. For stairs, lift lobbies, and other protected shafts, the objective is tenable access and egress. Excess pressure may need to be relieved, and every critical door should be verified under the relevant operating combinations. In short, the concept must be proven through coordinated controls, dampers, fans, HVAC interfaces, and field verification, not simply selected as a standard setting. This module, Section B of Module 12A, focuses on the architecture, equipment, and calculations that make a fire protection system work as an integrated whole. The emphasis is not on isolated components, but on the chain connecting them. Fire alarm coordination, firefighter controls, smoke control fans, dampers, VFD fire modes, sensors, standby power, and measurable proof. The learning path is straightforward, but each step must be verified. We begin with a confirmed zone, then issue a command to the appropriate device. That command should produce the intended physical response, such as moving air or changing equipment operation. Finally, we measure the result and prove that it meets the expected outcome. Verified zone, commanded device, physical response, accepted result. The four working ideas on this slide are command, move air, measure, and prove. Together, they create a practical framework for evaluating system performance. This section is designed to support client-ready training, with attention to both system architecture and the calculations needed to demonstrate that the installation performs as intended. This slide presents the core idea behind smoke control and HVAC interface design. The system must close the feedback loop. A fire input from the approved detection logic is only the beginning. The command path determines the operating mode through the FACP, while the FFCP or FSCS preserves manual priority for firefighters. Each command must also be supervised and time-stamped, so the sequence can be understood and verified. The air path then has to respond as an integrated system. Extract, makeup, supply, and pressurization fans work with fire and smoke dampers, relief paths, and rated shafts. During an event, normal HVAC operation becomes subordinate to the smoke control strategy. But commands and air movement are not enough on their own. The proof path confirms what actually happened in the field. That includes downstream power, fan run or fault status, damper end switch position, airflow, differential pressure, and door force. Standby power and event chronology complete the verification picture. In short, a reliable response requires agreement between the command, the air path, and the proof that both performed as intended. This slide focuses on proving that a smoke extract fan will perform as intended, not simply showing that the fan starts. The selected fan, ductwork, damper, rated shaft, and discharge path must achieve the approved operating point during fire mode, including operation on standby power. The key principle is real smoke movement, verified under the actual system conditions. Selection and installation should account for the required temperature and time rating, the complete fan curve with duct and terminal losses, and practical issues such as access, vibration, discharge, and maintenance. Control logic also matters. The fire mode command must bypass non-life safety limits where approved, while the design defines a standby fan or alternate response and preserves manual control at the firefighter's smoke control station. Acceptance testing then connects the whole sequence. We need to confirm downstream power, fan run and fault signals, damper position, airflow, and the pressure response on the fire floor. A failure alarm and synchronized chronology should show what happened and when. The system is accepted only when command, damper position, power, fan operation, airflow, and differential pressure all agree. This slide presents a supervised fire mode control architecture, organized around a digital twin and mission control blueprint. It distinguishes normal building management from fire response logic. Under normal BMS optimization, the system manages HVAC and energy efficiency. When the fire alarm or fire protection logic identifies an event, the sequence becomes more deliberate. Detect the condition, select the affected zone, and issue an automatic command. The important principle is that these actions are deterministic and supervised. The FSCS, or Firefighter's Smoke Control Station, provides manual control according to the adopted priority, so authorized personnel can oversee or adjust the response when needed. The architecture also shows how variable frequency drives are handled in fire mode. A VFD fire mode bypass can override normal efficiency behavior, but only within approved limits. Thermal limits and safety protections remain part of the control strategy, and short-circuit protection is not removed. In other words, the system can move from efficiency mode to an approved fire mode without abandoning the safeguards that protect the equipment. Safety remains active even when normal optimization is bypassed. Makeup air replaces the air removed by smoke control systems, but it must be introduced carefully. The key principle is controlled inflow below the smoke layer, without disturbing the fire plume or creating a path for smoke to spread. The air may come from outdoors or from an approved protected zone. The weather louver and its smoke exposure need to be assessed, and any shared path through the normal HVAC system must be positively controlled. Distribution is equally important. Use low-level, distributed openings, avoid directing air toward the fire or egress doors, and size the free area so the approved velocity is maintained. Excessive velocity can drive smoke, disrupt the plume, or increase door opening force. The system also needs proof of operation, not just design intent. Verify fan status, damper position, downstream power, capture hood or duct airflow, and opening velocity. Finally, confirm that pressure on the fire floor stays within its permitted limits. In short, introduce air low, distribute it broadly, control the velocity, and demonstrate that the complete system performs as intended. This slide focuses on stair pressurization, with one central objective: protect the egress path without making the doors difficult or impossible to open. A pressurization fan supplies air to the stair shaft, creating a pressure difference between the stair and adjacent floors. But that pressure is not designed in isolation. Supply airflow, leakage through the shaft and doors, relief paths, and the number of open doors all have to be solved as one system. The design basis should document leakage through the shaft, doors, and penetrations, while also accounting for stack effect and wind. The control strategy may use duty and standby equipment, or another approved resilient arrangement. Variable speed control is appropriate only when the equipment and sequence are reliable and listed, and pressure relief is essential to prevent overpressure. Acceptance testing measures differential pressure at representative doors and floors, open door airflow, and the force required to open each door. These tests must also be repeated with standby power and under fan failure conditions. In practice, success means maintaining smoke control performance while preserving safe, usable egress. This slide focuses on firefighter lift and lobby pressurization, with one central objective: preserve a protected response route. The lift shaft, vestibules, and protected lobbies must work together as a continuous boundary, especially at the fire floor. First, define the boundary clearly. That means coordinating the shaft, lobby, lift doors, service penetrations, relief paths, and adjacent fire floor interfaces. Recall operation and responder access also need to be coordinated, so the lift remains usable for firefighters when required. Next, verify the pressure relationship. The approved relationship between the lobby and shaft must be maintained, while uncontrolled air transfer through lift doors is avoided. Conditions at both the highest and lowest floors should be checked, because pressure behavior can vary across the building. Finally, the design needs objective proof. Confirm differential pressure, door opening force, and lobby tenability. Check fan and damper feedback, standby power, and clear indication at the firefighter's smoke control station or firefighter control panel. Manual override must also be available. The diagram reinforces that the fire floor, protected lobbies, and lift shaft operate as one coordinated smoke control system. This slide focuses on a critical verification principle for fire and smoke dampers. Position feedback must match the actual airflow effect. A command on the control system, or a graphic that appears to show open or closed, is not proof by itself. We need to verify actuator travel, blade position, end switch operation, and the resulting airflow or differential pressure response. The application has to be correct from the start. That means using the properly listed fire, smoke, or combination damper, and matching its orientation, velocity, temperature, and wall or shaft assembly. Access panels also need to remain usable for inspection and service. From a control perspective, the fail-safe position and power source must be documented, and smoke control dampers must follow the approved control matrix. Manual overrides cannot create an unsafe path. Finally, proof and maintenance include checking open and closed-end switches, stroke time, fault enunciation, links, seals, blades, actuators, and access. The complete sequence is what matters. Command, actuator movement, blade position, feedback, and the final zone response must all agree. This slide focuses on how a variable frequency drive, or VFD, should behave during a fire emergency. The central principle is that fire mode override must be intentional, approved, and supervised. A dedicated hardwired or supervised fire command can come from the fire alarm control panel or the firefighter's smoke control station. Once active, that command takes priority over normal building management optimization. The drive may bypass selected protective limits when necessary to preserve life-safety airflow, but the exact bypasses, priorities, and stop conditions must be defined in the approved design. Drive behavior also needs clear boundaries. Approved speed and acceleration, limited override of non-critical faults, and continued coordination of thermal, short circuit, and disconnect protection. The system then has to prove that the command produced the intended result. That means monitoring downstream power, output frequency or current, motor run status, and ultimately fan airflow or pressure. Faults, bypasses, and restoration should be time-stamped, with manual priority and the last approved command visible for review. In short, the system must command, execute, verify, and document fire mode operation. This slide focuses on the instruments and evidence needed to turn a commanded smoke control system into accepted, measurable performance. The central principle is that every critical value needs four things: a calibrated instrument, a defined measurement location, a stable operating mode, and evidence that is synchronized with the test. For pressure and force, I use a differential pressure meter across doors or barriers and a door force gauge at the approved handle location. Measurements should include the highest, lowest, and critical intermediate floors. For airflow and velocity, the appropriate tools may include a capture hood, duct traverse, approved flow station, or vane or hot wire anemometer at openings. I also record the damper position, fan speed, and door state because those conditions affect the result. Evidence discipline is what makes the reading defensible. Calibration certificates and serial numbers identify the instruments, while synchronized logs from the FACP, FSCS, BMS, and VFD connect the measurements to system events. Photos, readings, pass criteria, and authorized sign-off complete the test record. Together, these elements provide a traceable basis for acceptance. This module presents a practical design method for smoke control, fire ventilation, and HVAC interfaces. The central idea is that pressure, airflow, and door force must be solved together as one operating envelope, rather than as separate best-case calculations. For the pressure basis, Define both minimum and maximum differential pressure at every relevant boundary. Account for wind, stack effect, temperature, facade leakage, and both normal and standby power. The system also needs to avoid unstable hunting or excessive overpressure. Next, balance the full airflow path. Exhaust, makeup air, supply air, leakage, and relief all interact. Makeup air should remain below the smoke layer, with velocity checked in the direction of the fire. Dirty filters and degraded fans must be included, because those conditions can change the result significantly. Finally, verify door operability using the actual door size, closer, and hardware. Test both opening and self-closing in fire mode, including combinations of multiple open doors. If the doors become difficult to operate, correct the system rather than weakening life safety hardware. Acceptance is based on the measured operating envelope, not a single ideal point. This module focuses on a disciplined way to perform smoke control calculations without creating unnecessary analysis. The objective is to retain only the checks that can change a real design, control, redundancy, testing, or acceptance decision. Every input must be traceable, so the calculation can be reviewed, challenged, and defended. The learning path moves through 4 stages. First, I define the boundary. What system, zone, condition, and decision are actually being evaluated. Next, I calculate the flow using a useful hand check, enough to establish the governing relationships and identify obvious errors. I then compare that understanding with the exact model or the applicable original equipment manufacturer basis, rather than treating a complex result as self-explanatory. Finally, I challenge the assumed failure condition and witness the field result, confirming that the installed system responds as intended. This sequence connects analysis to evidence. It helps prevent both underchecking, where a critical assumption is missed, and overchecking, where detail consumes time without changing the outcome. The result is a focused, client-ready calculation process built around verification, traceability, and witnessed proof. This slide presents a disciplined way to use calculations in smoke control design. The governing principle is simple. Keep only calculations that change a real smoke control decision. First, define the boundary. Identify the protected zones and leakage paths, then freeze that boundary using coordinated as-built compartments. Next, calculate using an SI formula with substituted values, carrying dimensions and units through every line so the result remains traceable. Then challenge the design under the conditions that can change its behavior: fire, wind, stack effect, and credible failure cases. The review should consider both normal and degraded operation, with fault-tolerant thinking where failures are possible. Finally, accept the result using measured pressure, flow, and force supported by signed evidence. A calculation by itself is not acceptance. The installed system must be witnessed in normal, standby, and degraded modes, and the result should be retained only when it drives an engineering decision. This approach is aligned with the listed NFPA, IFC, Indonesian Code, and AHJ or Damker criteria. This slide shows how the criteria matrix turns different requirements into one governing design criterion. The formula is adopted code minimum plus an approved analysis target plus any equipment or listing limit. The plus sign means all applicable limits must be considered, and the approved governing criterion controls. The examples illustrate the distinction. For the smoke barrier, the IFC sprinklered minimum is 12.4 pascals, while the project fire floor target is 15 pascals negative. For airflow, the method is toward the fire, with a limit of 1.02 meters per second and a worked open door target of 1.00 meter per second. The clear layer requirement is 1.829 meters as an IFC minimum, compared with a 3-meter project target. The response criteria call for automatic mode to be established within 90 seconds. Duration is the greater of 20 minutes or 1.5 times the egress period. The key engineering decision is to label every value correctly: code minimum, project target, or worked example assumption. A training value must never be presented as a universal requirement. The governing references are the 2024 IFC and IBC provisions, where adopted, along with NFPA 92:2024. This slide defines the calculation basis for the approved design fire. The key point is that the fire is an explicit project input, not a value selected casually during analysis. We describe each scenario using 5 elements: location, fuel, suppression state, opening state, and a credible failure. For the base case, the scenario is a data hall equipment fire with a 5 megawatt worked cap. That 5 megawatt figure is an approved worked scenario, not a universal code value. Sprinklers are available, and the expected result is a controlled heat release rate, but no numerical suppression credit is taken without an approved basis. The opening condition is also defined. The fire door is closed and makeup air is open. Door open cases must be evaluated separately. For the failure condition, one duty component is unavailable while standby equipment operates. This is how Tier 4 continuity is tested, rather than simply assumed. The engineering decision is to replace the 5 megawatt placeholder with the approved fire engineering value, based on the fuel package, suppression response, and credible abnormal conditions. The governing references include NFPA 92, the 2024 IFC, and the approved fire analysis and hazard inventory. This slide defines the calculation behind the leakage register, which is the backbone of the pressure model. The governing relationship is Q leak equals CD times AEQ times the square root of 2 delta P over air density. In practical terms, leakage airflow depends on the discharge coefficient, the equivalent leakage area, the pressure difference, and the air density. The key engineering control is the component-by-component leakage schedule. The worked example separates the main leakage paths, rather than hiding them in one combined value. The fire zone uses an equivalent area of 3.00 square meters, representing walls, doors, dampers, and penetrations. The stair uses 0.5745 square meters, based on the stair wall and 10 door gaps. The lift shaft uses 0.749 square meters, including the shaft and landing doors. Finally, the lobby uses 0.227 square meters, representing closed doors and construction joints. Each area uses a discharge coefficient of 0.65. These values are transparent example inputs, so the model should retain sensitivity ranges and trace each component back to approved test data, enclosure leakage testing, and the coordinated BM model, consistent with NFPA 92:2024. This calculation determines the plume mass flow at the smoke layer interface, using the selected plume correlation. The governing equation combines 2 effects: the convective heat release rate and the height from the virtual fire origin to the interface. Here, the convective heat release rate, QC, is 3,500 kilowatts, based on the heat release split. The interface height is 3.0 meters, giving a height factor of 6.240. The cube root of the convective heat release rate is 15.183. Using those values, the entrainment term is calculated as 0.071 times 15.183 times 6.240, or 6.73 kilograms per second. The formula also includes the additional term 0.0018 times 3,500, which contributes 6.30 kilograms per second. Adding the 2 components gives a total plume mass flow of 13.03 kilograms per second at the 3.0 meter interface. The engineering decision is to use the plume regime and correlation that match the actual fire and its obstructions. If the configuration involves a balcony, wall, or line plume, this model is not appropriate, and a different correlation is required, consistent with NFPA 92/2024 and the approved fire engineering analysis. This slide converts the smoke plume mass flow into a hot, volumetric flow rate for design purposes. The governing relationship uses the ideal gas approximation. Smoke density equals absolute pressure divided by the gas constant times absolute smoke temperature, and volumetric flow equals mass flow divided by density. Here, the smoke temperature from the plume energy balance is 570.4 Kelvin. Using an absolute pressure of 100,800 pascals and a specific gas constant of 287.05, the calculated smoke density is approximately 0.616 kilograms per cubic meter. The plume mass flow at the layer interface is 13.03 kilograms per second. Dividing that mass flow by the calculated density produces 21.16 cubic meters per second of hot smoke flow. That value is the base exhaust quantity before any additional allowances are applied. The key engineering point is to keep mass flow and volumetric flow distinct. Fan and duct ratings must be based on a consistent temperature and density, otherwise the equipment selection may not represent the actual hot smoke conditions. The calculation follows the cited NFPA 92, 2024 guidance, the ideal gas relation, and AMCA 210-25. This slide establishes the design extract duty for the fire mode. The governing value is 32.0 cubic meters per second, or M superscript 3/S. The calculation selects the greatest applicable value from three possible checks: layer control, pressure balance, and post-fire purge, when that purge is applicable. The layer control method, based on the approved zone or CFD result, gives 32.0 cubic meters per second. The pressure balance method reaches the same result by combining 22.00, 9.92, and 0.08 cubic meters per second for makeup flow, leakage, and residual flow. The post-fire purge is different. Its 6 air changes per hour recovery screen produces 21.0 cubic meters per second, but that is a separate recovery mode, not the fire extract duty. Taking the maximum of 32.0, 32.0, and 21.0 therefore confirms a governing fire duty of 32.0 cubic meters per second. The engineering decision is to carry that value forward because the approved layer control and pressure balance methods converge. During commissioning, flow and pressure should be verified together, with the design supported by NFPA 92:2024, the approved smoke control analysis, and the project sensitivity register. This slide checks the fire floor air balance using the residual method. The governing relationship is the sum of inflows minus the sum of outflows. In this case, the mechanical inflow is the makeup air at 22.00 cubic meters per second, while the mechanical outflow is the extract at 32.00 cubic meters per second. We also account for infiltration into the floor. At a pressure of 15 pascals and a leakage area of 3.0 square meters, that inflow is calculated as 9.92 cubic meters per second. So the residual is 22.00 plus 9.92 minus 32.00, which equals negative 0.08 cubic meters per second. The balance closes within the approved plus or minus 0.10 cubic meters per second tolerance. The negative sign indicates a small net outflow, but it remains within the worked acceptance limit. The engineering decision is not to treat this single floor calculation as the complete building solution. Instead, a network solver should be used for the full building, followed by balancing the installed variable frequency drives and dampers, so the measured residual meets the approved tolerance. The governing reference is NFPA 92:2024, together with the approved multi-zone pressure model and testing, adjusting, and balancing procedure. This slide defines the pressure calculation for the fire floor extract and makeup system. The key design choice is a fire floor pressure of negative 15 pascals relative to the adjacent protected space. The calculation begins by selecting the greater of the applicable code minimum and the approved analysis target. Where 2024 IFC Section 909.6.1 applies to a sprinklered smoke barrier, the code screen is 12.4 pascals. The project adopts 15.0 pascals, which provides a 2.6 pascal design margin above that minimum. The pressure sign is important. The relationship is fire zone pressure minus adjacent space pressure, so a result of negative 15 pascals means air is intended to move toward the fire zone. For control purposes, the illustrative band is plus or minus 3 pascals around the target, or negative 12 to negative 18 pascals. The final tolerance must come from the approved test script. The engineering decision is to commission the fire floor at negative 15 pascals under the defined door and damper conditions, while confirming that door forces and airflow limits are not exceeded elsewhere. The governing references are the 2024 IFC, NFPA 92:2024, and the approved analysis and acceptance criteria. This slide works through the leakage flow calculation for the fire floor extract and makeup system. The governing relationship is CLEAK equals CD times EQ times the square root of 2 delta P over rho. In practical terms, that combines the discharge coefficient, the equivalent leakage area, the pressure difference, and the air density to estimate the airflow entering through leakage paths. The coefficient is taken as 0.65, representing an aggregate sharp edge approximation. The controlled leakage register provides an equivalent leakage area of 3.00 square meters. At a pressure difference of 15 pascals and an ambient air density of 1.159, the pressure term evaluates to 5.088 meters per second. Multiplying these values gives 992 cubic meters per second of leakage flow. That result is a worked orifice estimate, not a substitute for verification. The key engineering decision is to confirm the 3.00 square meter assumption using component data and enclosure testing. A leakage variation of plus or minus 20% can materially change both the pressure response and the required makeup airflow. The governing reference is NFPA 92/2024, together with approved leakage testing and door and damper leakage data. This slide shows the calculation used to size the fire floor makeup openings. The governing relationship is simple. Net free area equals volumetric airflow divided by the average velocity through the certified free area. Here, the selected makeup duty is 22.0 cubic meters per second, and the worked project opening target uses a face velocity of 5.0 meters per second. That produces 40 square meters of net free area. The area is then distributed across 8 equal grills, giving 0.55 square meters of effective free area per grill. This arrangement is intended to keep the local approach velocity near the adopted 5 meter per second value, rather than concentrating the airflow in one location. There is an important design distinction here. The 5.0 meters per second is a worked project opening target, not a code requirement stated by this calculation. In the final design, I would use certified free area, not nominal grill dimensions, and verify the local approach velocity toward the fire remains within the adopted limit. The governing references include NFPA 92, the applicable 2024 IFC or IBC section 909.7 where adopted, and exact manufacturer data for the selected louvers or grills. This calculation establishes the corrected closed stair leakage total used for the pressurization analysis. The governing relationship is the total equivalent leakage area, which combines wall leakage with the leakage from all closed door gaps. Wall area, plus the number of doors multiplied by the gap area for one door. For the enclosure, the 910 square meter stair area is multiplied by the stair leakage ratio of 0.00035, producing a wall leakage area of 0.3185 square meters. The closed door case includes 10 doors, each with a gap area of 0.0256 square meters. Together, those doors contribute 0.2560 square meters. Adding the two components gives 5,745 square meters, the corrected total leakage area. The discharge coefficient is set at 0.65, representing the aggregate orifice approximation used in the calculation. From an engineering standpoint, the wall and door entries should remain separate in the leakage register. That separation allows commissioning teams to determine whether a pressure shortfall is related to construction leakage or to door condition. The calculation is referenced to the adopted 2024 IFC and IBC section 909.5, NFPA 92:2024, and the approved stair leakage register. This slide works through the all doors closed airflow calculation for the stair pressurization system. The governing relationship is Q closed equals the discharge coefficient, multiplied by the equivalent leakage area, multiplied by the square root of 2 times the pressure difference divided by air density. Here, the equivalent leakage area for all 10 doors closed is 0.5745 square meters, and the project's closed door pressure target is 50 pascals. Using the stated ambient air density, the velocity term evaluates to 9.288 meters per second. Applying the coefficient of 0.65 and multiplying these values gives a corrected airflow of 347 cubic meters per second at 50 pascals. The engineering implication is important. The worked 7.5 cubic meter per second fan cannot remain at full output when all doors close. It must turn down to approximately 3.5 cubic meters per second, or a coordinated relief path must open. This calculation supports the VFD closed door set point and is tied to the approved stair pressure criteria and fan sequence referenced in NFPA 92:2024. This calculation determines the required supply duty for the stair pressurization system in the two open door case. The governing relationship combines two components: airflow needed through the open doors and additional airflow required to overcome leakage through the walls and the 8 remaining closed door gaps. First, the remaining leakage area is calculated as 0.3185 plus 8 times 0.0256, giving 0.5233 square meters. At a pressure difference of 50 pascals, and using the stated discharge coefficient and air density, that leakage requires approximately 3.16 cubic meters per second. Next, the two open doors require 4.20 cubic meters per second, based on 2 doors and an airflow velocity of 1.00 meter per second. Adding these values gives 7.36 cubic meters per second, which is rounded up to 5 cubic meters per second as the selected commission duty. The engineering decision is to select and balance that duty, then verify closed door pressure, relief performance, airflow direction, and force limits. The calculation follows the cited NFPA 92 and adopted 2024 IFC and IBC provisions. This slide shows how we screen stair pressurization pressures before moving to a full engineering analysis. The door pressure is the combined result of fan pressure, stack effect, wind, and fire or system interaction. Our nominal fan target is 50.0 pascals. For the initial stack screen, we use a midpoint neutral plane estimate of plus or minus 10.5 pascals. That produces a low stack-only condition of 50.0 minus 10.5, or 39.5 pascals. At the high end, 50.0 plus 10.5 gives 60.5 pascals. The important point is that the stack-only range runs from 39.5 to 60.5 pascals. The low condition remains above the 12.4 pascal screen, while the high condition approaches the 62.6 pascal maximum associated with door force. That means the fan target cannot be evaluated in isolation. Wind must be treated as a signed effect that varies by facade and floor, rather than being added uniformly. The engineering decision is to use floor-by-floor network or CFD results, supported by multiple sensors, and to check the design against the approved shaft pressure network and door force criterion in NFPA 92:2024. This slide works through the maximum pressure calculation for the stated 133 Newton door. The governing relationship compares the total opening force limit with the force already consumed by the closer, latch, and hardware, then accounts for the handle distance and door width. Here, the adopted limit is 133 newtons, while the measured hardware contribution is 60 newtons. That leaves 73 newtons available at the handle. Using the shown dimensions, a 0.90 meter handle distance, a 2.10 meter door width, and a 0.50 meter lever arm factor, the calculation is 73 times 0.90 divided by 2.10 times 0.50. The result is 62.6 pascals, which is the maximum pressure difference for this specific door and criterion. The nominal design target should remain below that value. The important engineering decision is not to treat 62.6 pascals as a universal limit. If the hardware force, door width, handle location, or handle radius changes, the pressure must be recalculated. The applicable references include the 2024 IBC where adopted, NFPA 92, accessibility requirements, and the door schedule. This slide works through the pressure calculation for stair pressurization, using full fan flow immediately after 2 doors close. The governing relationship predicts steady pressure from fan airflow, discharge coefficient, air density, and the combined area of fixed leakage and effective relief opening. With a fan flow of 7.5 cubic meters per second, the existing 0.40 square meter relief is combined with 0.5745 square meters of closed stair leakage. Using the stated values, the predicted pressure is 81.2 pascals. That exceeds the 62.6 pascal door force limit, so the worked 0.40 square meter relief is rejected. Increasing the relief area to 0.55 square meters produces a preliminary calculated pressure of 61.0 pascals, which is below the force limit. However, this is not yet an acceptance result. The effective opening area must be verified, along with variable frequency drive response, and the fail-safe transient immediately after the doors close. The engineering decision is therefore to reject 0.40 square meters for this case, and coordinate the 0.55 square meter option against the approved transient model, damper manufacturer data, and NFPA 92:2024. This slide brings the lobby airflow calculation together for the lift shaft and lobby scenario. The formula selects the fan flow by applying the documented project margin to two components: airflow through the open door, plus leakage through construction joints and doors that remain closed. The remaining leakage calculation is shown as 0.94 cubic meters per second, including the joints and two closed door gaps at 30 pascals. The open door contribution is 1.575 cubic meters per second, based on an airflow velocity of 0.75 meters per second. Adding those two values gives a defined scenario subtotal of 2.515 cubic meters per second. Applying the 15% selection margin produces 2.89 cubic meters per second, which is rounded to the corrected selection of 3.0 cubic meters per second. The engineering decision is equally important. Provide two 100% lobby fans, or another approved fault-tolerant arrangement, and demonstrate automatic duty-to-standby transfer. That arrangement must align with the approved redundancy and cause-and-effect criteria referenced in NFPA 92/2024. This calculation shows how pressure changes through the lift shaft and lobby move air toward the fire floor. The governing relationship is straightforward. Pressure difference equals upstream pressure minus downstream pressure. From the stair to the lobby, the calculation is plus 50 minus plus 30, giving 20 pascals. That represents the protected zone transfer. From the lobby to the fire floor, plus 30 minus negative 15 produces 45 pascals, which is the key airflow path toward the fire. The adjacent to fire condition is plus 10 minus negative 15, or 25 pascals, providing the smoke barrier pressure. The slide also checks whether the lobby door can still be opened. Using the pressure, door area, and a force allowance, the result is 112.5 newtons, which is below the 133 newton example limit. The engineering decision is therefore conditional, not automatic. Accept this pressure cascade only if every critical door remains openable and measured airflow direction matches the approved smoke model. The governing references are NFPA 92:2024, the 2024 IFC Section 909, and the adopted door force criterion. This slide shows the worked fan duty calculation for the duct system. The governing relationship is that fan design pressure equals straight duct friction, the sum of device losses, terminal loss, system effect, and any documented allowance. For the straight duct, the calculated friction loss is 21.7 pascals. The fittings and other devices contribute 155.8, 80, and 120 pascals, for a combined 355.8 pascals. Adding those values gives a system subtotal of 377.5 pascals at the stated air density. The project then applies a documented allowance of 75.5 pascals. That brings the calculated requirement to 453.0 pascals, which is rounded for the work selection to 500 pascals. This is a project calculation, not a code-prescribed factor. The engineering decision is therefore to select and test the fan at 32 cubic meters per second and 500 pascals, using the same density and temperature basis as the system resistance calculation. The selection should be checked against NFPA 92, AMCA 210, the approved fan schedule, and the completed resistance calculation. This slide shows how the selected fan point is checked against the required fire mode duty. The required operating point is 32.0 cubic meters per second at 500 pascals. Using the system curve, the pressure required at 35 cubic meters per second is approximately 598 pascals, represented by the K times 35 squared relationship. The selected fan has a certified catalog point of 35 cubic meters per second at 600 pascals at the stated standard air density. That means the selected point meets and slightly exceeds the system requirement at the higher flow. To trim operation back to the required airflow, the variable frequency drive is set to a speed ratio of 32 divided by 35, or about 91.4% speed. The key engineering decision is proving a stable operating point away from stall. Commissioning must demonstrate that both the duty and standby fans deliver the same measured result. The calculation is supported by the system curve, the certified fan curve, and the project selection report, with AMCA 210-25 and NFPA 92:2024 as the governing references. This slide focuses on a critical calculation rule. The fan and the system must use the same temperature and density basis. For the mixed duct condition, the temperature is 120 degrees Celsius, or 393.15 Kelvin. This is separate from the 297 degrees Celsius plume interface, so those two conditions should not be combined. Using the ideal gas relationship, hot air density is calculated from absolute pressure, the gas constant, and absolute temperature. At the stated conditions, the hot density is approximately 0.893 kilograms per cubic meter. Compared with standard air at 20 degrees Celsius, or 1.204 kilograms per cubic meter, that gives a density ratio of 0.742. That ratio converts a 500 pascal pressure value on the standard air basis to an equivalent hot air pressure of about 371 pascals for the same geometry and volume flow. The engineering decision is to normalize both the fan and the system consistently. We should use the manufacturer's certified temperature correction method, along with the rated fire temperature and duration, rather than correcting only one side. The governing references are AMCA 210-25, NFPA 92:2024, and the applicable fan listing and OEM data. This slide shows the calculation for the emergency running minimum for the duct, fan, and power system. The connected fire mode loads total 57.5 kilowatts, combining the extract system, stair, lift, lobby, and controls. We then apply a 15% demand allowance, bringing the real power requirement to 66.1 kilowatts. To convert that figure into apparent power, we divide by the stated power factor of 0.90. The result is 73.5 kVA, which is the worked emergency running minimum. The duration calculation is separate. It uses the greater of 20 minutes or 1.5 times the approved egress time. With the example egress time of 12 minutes, that produces 18 minutes, so the governing duration remains 20 minutes. This is a running screen only, not the final source rating. Final capacity still depends on starting performance, harmonics, voltage, ATS and cable conditions, coordination, and concurrent load studies. Those decisions should be checked against the cited 2024 IFC provisions, NFPA 92, and the approved emergency power study. This calculation establishes whether the common clock field proof meets the approved end-to-end time limit. The governing formula is TE2E equals stable proof time minus input time, with a pass when that result is less than or equal to the approved limit. Here, the synchronized FACP, or FATSU, accepts the initiating input at 0.0 seconds. Interim commands are timestamped for diagnosis, but they are not added together, because overlapping actions would inflate the elapsed time. The controlling endpoint is the last stable proof from the slowest mandatory field device, such as a fan, damper, or pressure condition. That proof occurs at 77.0 seconds, producing an end-to-end result of 77.0 seconds. Compared with the 90-second limit, the worked margin is 13.0 seconds. The engineering decision is therefore a preliminary pass, provided the team proves the slowest mandatory field state from one synchronized input clock, rather than relying only on the panel command. The governing references are the 2024 IFC, Section 909.17, NFPA 72 from 2025, NFPA 92 from 2024, and the approved cause and effect documentation. This slide demonstrates how a pitot traverse confirms the main duct airflow, using measured conditions rather than relying only on the fan duty rating. The calculation starts with an area-weighted average velocity pressure of 40 pascals, a calibrated pitot coefficient of 0.99, and an actual air density of 1.159 kilograms per cubic meter. Applying those values gives a site-corrected air velocity of 8.22 meters per second. We then multiply that velocity by the duct area, 4.00 square meters, to obtain a measured flow of 32.9 cubic meters per second. The key result is that the measured flow is 2.8% above the 32.0 cubic meter per second duty point. That result is acceptable only if the traverse itself is technically valid. The measurement plane must be suitable, the instruments must be calibrated, the density correction must be documented, and the approved testing, adjusting, and balancing method must be followed. The governing references shown here include the 2024 IFC and IBC Section 909.18, AMCA 203 for field measurement, AMCA 210 for the certified fan basis, and the approved tab procedure. This slide quantifies the uncertainty associated with the airflow measurement. The combined standard relative uncertainty, shown as U sub C, Q, is calculated by taking the root sum square of four independent components: velocity or traverse profile, area measurement, instrument and calibration, and air density. The largest contribution is velocity, at 5%, reflecting how thoroughly the airflow profile is traversed. Area measurement contributes 2%, instrument accuracy and reading contribute another 2%, and density contributes 1.5%. Combining these by RSS gives a result of approximately 5.9%. The calculation shown, square root of 35.25, produces 5.94%, reported here as a standard uncertainty rather than an expanded uncertainty. The engineering implication is important. Acceptance tolerances should be wider than the quantified measurement uncertainty, while still maintaining enough margin to the design criterion. In other words, a pass or fail decision should not be based on a difference smaller than the uncertainty of the measurement itself. This approach follows the approved uncertainty budget and commissioning plan, with reference to BIPM JCGM 100 and AMCA 203 and 210. This slide works through a representative purge calculation for a data hall, using a volume of 12,600 cubic meters and an approved recovery input of 6 air changes per hour. The basic airflow relationship is Q purge equals N times V divided by 3,600. Substituting those values gives a purge airflow of 21.0 cubic meters per second. That figure is separate from the 32 cubic meters per second smoke extract rate, so the two should not be treated as interchangeable. The concentration model assumes ideal, well-mixed conditions. C over C0 equals e to the negative nt. Solving for 1% of the initial concentration gives t equals the natural logarithm of 100 divided by n, or 4.605 divided by 6 hours. The result is about 0.768 hours, or 46.1 minutes. 6 ACH gives an ideal 46-minute time to 1%, not guaranteed atmospheric clearance. Use this number only as a recovery screen. Actual reentry and HVAC restoration depend on measured conditions, fire service and authority approval, and the approved recovery procedure, with NFPA 92 and the applicable adopted edition of NFPA 2001 governing the process. This slide focuses on the interfaces and command boundaries that connect smoke control with the broader fire protection system. The central idea is that every connected system retains its own life safety function, while smoke control logic coordinates how commands are issued, prioritized, verified, and restored. The sequence is detect, select, command, verify, and coordinate. At the fire alarm and smoke control panels, The fire zone input drives the smoke control matrix. The system must support automatic commands, firefighter priority, and mismatch alarms. HVAC and the building management system may have dedicated or non-dedicated fire modes, but normal optimization always remains subordinate to life safety. Trends can support troubleshooting, but they do not replace field verification. Lift, access, and voice systems coordinate recall, firefighter lift operation, protected lobby response, door states, and emergency messaging. Finally, power and monitoring confirm emergency or standby source availability, ATS status, fan operation, damper position, and differential pressure or airflow feedback. Together, these interfaces create a controlled chain from detection to confirmed system performance. This slide defines the control sequence for smoke control, fire ventilation, and HVAC interfaces. The central idea is that every fire scenario must end with measurable proof, not just a command sent from a panel. The sequence begins with the fire input. The system identifies the verified zone, along with adjacent or protected zones, then applies the appropriate zone logic. That logic selects the required fans, dampers, and fire modes, while recording both the command and the expected equipment state. The next step is field proof. We verify downstream power, damper position, and fan operation, then compare actual airflow, differential pressure, and door force against the acceptance criteria. Any mismatch or timeout must be enunciated clearly, so an incomplete response is not mistaken for a successful one. Finally, firefighter control follows the adopted priority. Reset is permitted only after the area is safely cleared and inspected. Normal HVAC is then restored sequentially, rather than all at once. This zone-by-zone traceability connects the fire input to system behavior, field evidence, failure reporting, and a controlled return to normal. This slide focuses on a central principle of smoke control and HVAC interface design. Every failure mode needs an explicit fallback and clear operator authority. Acceptance testing must go beyond the successful automatic sequence. It should deliberately include failed starts, failed damper positions, power loss, sensor loss, and manual override cases. Equipment failures can include a duty smoke extractor makeup fan that does not start, a tripped VFD, a damper that fails to reach position, a drifting or lost pressure signal, or a local disconnect left open. Control and power failures create additional risks. The standby source may be unavailable. Communications between the fire alarm control panel and smoke control station may fail, or the BMS display may disagree with hardwired proof. Unsynchronized event timestamps can also complicate diagnosis and accountability. The safe response is specific and disciplined. Enunciate the failed component, start standby equipment, or execute the approved alternate mode, and preserve egress and responder control. Escalate the impairment, establish a fire watch when required, and retest the system before returning it to normal service. These safeguards turn failure handling into a planned operational capability, rather than an improvised response. This module moves from theory into applied scenarios, where the goal is to respond correctly when a fire protection system does not behave as expected. The focus is not simply on identifying a problem. It is on following a disciplined path from the initial event to an authorized recovery, without creating a second smoke path or making the situation harder to control. The learning path is shown as 5 connected steps. First, identify the event. Next, confirm the commanded mode, or what the system was instructed to do. Then measure the actual response, rather than assuming the command produced the intended result. Based on that measured response, the operator makes a decision using the approved zone model. If necessary, the operator executes a fallback and finally restores the system through the authorized recovery process. The key principle is measure before deciding. That sequence keeps actions evidence-based, supports consistent operator judgment, and provides a clear structure for examining failures and restoration in the scenarios that follow. This scenario follows a fire on a high-rise data hall floor, with the smoke control response organized as a clear sequence: alarm, zone selection, exhaust, shaft protection, and measurement. The central objective is to keep the fire floor controlled negative while preserving the approved positive relationship for protected egress and responder zones. On the fire floor, The system opens the smoke extract path, starts the duty fan, introduces controlled low-level makeup air, and stops conflicting normal recirculation. At the same time, adjacent floors and egress areas receive their approved response. Stairs and the firefighter lift lobby or shaft are pressurized, while doors remain usable and responder access is maintained. The response must also be proved, not simply commanded. Verification includes fan status, VFD output, damper end switches, pressure difference, airflow, door force, standby power, and the event chronology. During recovery, firefighter manual control remains available. The smoke control state stays active until clearance, and restoration follows only the approved sequence. These checks connect system operation with safe, documented performance. This scenario focuses on a smoke extract fan that receives a command, but fails to deliver the required run signal or airflow. The key principle is that the operator responds to measured performance and the approved fallback procedure, not to a graphic symbol alone. The sequence begins by detecting the fault and checking the evidence. That includes confirming the command is present, then checking the VFD, disconnect, fire or smoke damper, and downstream power. If the duty fan still cannot achieve performance, the system should start the standby fan or another approved path, while announcing the failed unit and any response timeout. The operator or firefighter then selects the approved manual command, protects stairs and lobbies, and restricts entry into unsafe areas. The response is not complete until the event is documented. Capture the failure and fallback chronology, repair the equipment, retest the system, and restore the normal lead and lag arrangement. Measured performance, approved fallback, and documented recovery are the controls that make this response reliable. The abbreviations at the bottom identify the key interfaces, including the FFCP, FSCS, fire and smoke dampers, differential pressure, and VFD. This scenario addresses a fire or smoke damper that fails its position proof. The key point is that I do not treat the graphic symbol on a control screen as proof that the damper is where it should be. I respond to measured performance and to the approved fallback procedure. The sequence is straightforward. Issue the command, allow the defined timeout, confirm the alarm, isolate the affected path, and then recover. Fault evidence can include a commanded position that does not match the end switch or airflow and differential pressure, showing that the intended path has not been achieved. The automatic response should identify the exact damper and zone, then start the approved alternate path, or stop a conflicting fan. If manual control is necessary, I first understand the consequence for that zone. I also protect egress and firefighter access. Recovery is not complete after the actuator moves. I inspect the actuator, blades, linkage, and any obstruction, then stroke and time the damper, and prove the resulting airflow effect before returning it to service. Measured performance, not the symbol alone, is the basis for action. This scenario addresses a stair or lobby that has become overpressurized, making a door difficult to open. The key point is that the operator responds to measured performance and the approved fallback, not to a graphic symbol alone. First, confirm the fault evidence. Differential pressure and opening force exceed approved criteria, or the relief and modulation functions are unavailable or incorrect. The automatic response may open the approved relief path or trim the pressurization fan, while still retaining the minimum required protection at remote floors. The operator or firefighter then checks the actual door enclosure, including the open door condition. Life safety hardware must not be disabled simply to make the door easier to operate. After the adjustment, verify the door, measure conditions again, and recover the system in a controlled way. Record differential pressure and door force at both high and low floors. Finally, correct the balancing or relief problem and repeat all relevant operating combinations, so the result is demonstrated rather than assumed. This scenario addresses a critical failure condition: power, the VFD fire mode, or the control path is lost. The central principle is that the operator responds to measured performance and an approved fallback strategy, not to a graphic symbol alone. The sequence is detect, transfer, direct, fall back, and recover. First, establish the fault evidence. Confirm whether the command is failing to reach the drive or motor, and check the ATS, feeder, VFD input and output, and disconnects. If automatic response is available, the system transfers to the standby source and approved fire mode, while enunciating the component that is actually unavailable. The operator or firefighter then uses hardwired or manual control according to the adopted priority. The immediate objective is to maintain protected zones with whatever equipment remains available. Recovery is not complete when equipment simply starts again. Capture the ATS, VFD, run, and airflow chronology, then prove both normal and standby modes after repair. This evidence connects the failure, the response, and the final verification. This slide presents the interface and evidence matrix for smoke control, fire ventilation, and HVAC systems. The central idea is that every mapped point must connect 4 questions. What was commanded, what physically happened, what was measured, and who had authority to override or restore the system. The evidence must show the complete chain from command to verified outcome. Under commands, we track fire zone selection, smoke control mode, fan operation and approved speed, damper or relief position, HVAC shutdown or fire mode override, and manual commands from the FSCS. Feedback and measurement then confirm downstream power, ATS and disconnect status, VFD output, fan run or fault condition, airflow, damper end switches, stroke timing, differential pressure, opening velocity, and door force. The FACP, BMS, and VFD chronology must also align. Finally, authority and recovery define who can take priority, how impairments are handled, and what fallback actions apply. Automatic selection and latching, firefighter manual priority, approved purge, authorized restoration, and retesting all need documented evidence. This matrix turns system interfaces into an auditable sequence rather than assumptions. Return to normal is not an automatic reset. It is a controlled restoration sequence, and normal HVAC remains subordinate until the fire zone is formally released and conditions are proven safe. The process begins with the preconditions. Confirm fire service or AHJ clearance where applicable. Verify that there is no clean agent retention or hazardous atmosphere restriction, and inspect doors, dampers, shafts, and fire stopping. Once those conditions are satisfied, the authorized person releases any manual overrides. Smoke control fans are then stopped in the approved order, followed by restoration of normal HVAC, pressure, and access states. The final step is verification and closeout. Prove that normal and standby systems are ready, supervised, and operating as intended. Any defects remain open until they have been retested and cleared. Finally, preserve the logs, readings, and authorization record so the restoration can be demonstrated later. This sequence applies across the FFCP, FSCS, fire and smoke dampers, differential pressure controls, and variable frequency drives. The objective is a safe, documented return to normal, not simply turning systems back on. This module focuses on Section E, commissioning, integrated testing, and evidence for the data center fire protection system. The goal is not simply to show that equipment operates, but to produce measured, witnessed proof under the conditions that matter. We examine pressure, airflow, door force, equipment feedback, fallback, and restoration during normal, standby, and failure conditions. The central learning path is approved script, calibrated instrument, stable mode, measured proof, and signed record. The 4 stages shown here are FAT, or Factory Acceptance Testing, SAT, or Site Acceptance Testing, IST, or Integrated Systems Testing, and the evidence that connects all 3 into a client-ready record. Each stage should build confidence in the next, while keeping the test method controlled and repeatable. The final result is more than a successful demonstration. It is documentation that shows what was tested, how it was measured, under which condition, and who witnessed or accepted the outcome. That discipline makes commissioning defensible, traceable, and ready for handover and training. This slide shows the commissioning path from analysis to integrated performance. The sequence begins with design and factory acceptance testing, or FAT. At this stage, the approved analysis, zone matrix, point schedule, and control logic are reviewed, while the fan, VFD, damper, and panel responses are simulated. Instrument locations and pass criteria must also be established before field work begins. Static testing and site acceptance testing, or SAT, then confirm that the installed equipment operates as intended. That includes rotation, damper stroke, local controls, power and automatic transfer switching, VFD fire mode, feedback signals, and initial balancing. Calibration records are part of this evidence. Integrated systems testing, or IST, moves from individual components to real operating scenarios. Teams verify zone performance, credible failures, manual control, and pressure and door behavior at the fire floor, stairs, and lobbies. The final handover includes signed defect records, test documentation, and operating procedures. The objective throughout is to demonstrate the approved pressure under normal power, standby power, manual control, and failure conditions. This slide distinguishes three test families that prove different layers of the same smoke control and fire ventilation safety function. A successful panel simulation does not prove that air moved correctly or that a door remained usable in the installed building. FAT, or factory acceptance testing, focuses on logic in panels before installation. That includes point schedules, labels, graphics, zone selection, latching and priorities, fire mode and fault simulation, manual overrides, reset logic, and any recorded deviations. SAT, or site acceptance testing, verifies the installed equipment. The team checks fan rotation, performance and vibration, VFD fire mode, feeders and standby power, damper travel and end switches, sensor calibration, and the initial airflow and pressure balance. IST, or integrated systems testing, evaluates the complete response across fire, adjacent, and protected zones. It measures differential pressure, airflow, opening velocity, and door force, while also testing duty failure, standby start, manual priority, power transfer, recovery, and synchronized evidence for acceptance. Together, FAT, SAT, and IST create a chain of evidence from programmed logic to real building performance. Before the witness test begins, the measurement layout must be fully defined. Every reading needs a clear measurement point, operating condition, pass criterion, time source, and responsible witness. For pressure and door stations, the test drawing should identify differential pressure taps across each critical barrier, including the highest, lowest, and representative intermediate floors. Door force is measured at the approved handle location, while the team records whether the door is open or closed, confirms the closer condition, and observes self-closing and latching. Airflow and velocity stations require the selected method to be clear, whether that is a duct traverse, capture hood, or listed flow station. The layout also identifies make-up opening velocity grids, smoke extract and pressurization discharges, damper positions, and VFD speeds. Readings should be taken only after conditions stabilize. Finally, the evidence package must connect each result to an instrument ID and calibration certificate. Align the FACP, FFCP, FSCS, BMS, VFD, and ATS clocks, then record the command, feedback, and reading with photographs, witness details, defects, and retest information. This slide presents an example witness test script for fire floor smoke control performance. The central principle is controlled, documented verification. Before testing, I confirm the approved fire zone, the door conditions, and the normal HVAC state. I also install calibrated instruments for differential pressure, airflow, and velocity, then synchronize the control and event logs so every action can be traced accurately. During execution, I initiate the verified zone input and observe the complete response. That includes exhaust systems, make-up air, fire and smoke dampers, and the protected shafts. Once conditions stabilize, I measure airflow, differential pressure, velocity, and door force. The goal is not simply to see equipment operate, but to demonstrate that the system performs as designed under the test condition. Finally, I compare every reading with the approved acceptance criteria. I verify system feedback, standby power, and firefighter control through the firefighter's smoke control station. Any defect is recorded with its corrective action, followed by a witnessed retest. This process creates a clear, auditable record from preparation through final acceptance. This slide presents an example test script for stair pressurization, covering both closed-door and open-door design cases. The central idea is that the test must be controlled, witnessed, and repeatable, using an approved script, calibrated instruments, synchronized logs, and clearly defined abort criteria. The objective is to demonstrate safe performance under the actual design conditions, not simply to capture one pressure reading. Preparation begins by balancing the shaft and verifying relief and control settings. The team should identify the highest, lowest, and other critical doors, then establish baseline closer force measurements. During execution, test the all-closed condition at minimum and maximum differential pressure. Next, open the approved design doors and measure airflow, the remaining differential pressure, and the force required to open each door. The final stage is proving and recording the results. Confirm that egress doors open, self-close, and latch properly. Repeat the test for standby power and fan failure conditions, and document every door, floor, system state, and result. The abbreviations at the bottom identify the key smoke control and HVAC interface components used in the test records. This slide outlines a practical test script for a firefighter lift shaft and its protected lobby. The central idea is that the test must be controlled, witnessed, and fully traceable, using calibrated instruments, synchronized logs, and clear abort criteria before anyone begins. Preparation is the first critical stage. We confirm lift recall, lobby doors, and shaft interfaces, then install differential pressure instruments at the selected floors. We also verify that the firefighter control panel is showing the expected indications. During execution, we initiate representative fire floor scenarios and measure the pressure relationships between the lobby, the floor, and the lift shaft. At the same time, we operate the doors and firefighter manual controls, so the test reflects the decisions and actions required in an actual event. The final stage is to prove performance and preserve the evidence. We confirm door force and protected access, verify fan and damper feedback along with standby power, and record the complete chronology from recall through smoke control operation and system restoration. The abbreviations at the bottom provide a common reference for the control panel, smoke control station, dampers, pressure measurements, and variable frequency drives. This slide presents a structured test for smoke control fan failure and the system's fallback response. The purpose is not simply to trigger a fault, but to prove that the fire mode strategy remains safe and controllable when a primary fan or drive becomes unavailable. Preparation comes first. I would confirm whether the approved strategy uses a duty and standby fan or another alternate arrangement, then establish normal fire mode performance. Before any failure is injected, the team must agree on safe test boundaries and clear abort conditions. During execution, we remove the run proof, trip the VFD, or open an approved test circuit, depending on the method authorized for the system. We then observe the timeout, fault annunciation, and fallback sequence, while measuring pressure and airflow throughout the transition. The final step is to prove and record the result. I would confirm that protected zones remain within the required safe response, verify firefighter manual control at the FSCS, then restore the system, clear the alarm, and repeat the readiness proof. Every action should be supported by an approved witness script, calibrated instruments, synchronized logs, and explicit stop criteria. This example test script focuses on proving that smoke control dampers, fire mode variable frequency drives, and downstream power interfaces operate together as intended. The central principle is traceable proof, not just a successful command. Before testing, I identify every critical damper, VFD, and feeder, then verify access, labels, fail positions, and available test points. I also align the time sources for the fire alarm control panel, building management system, VFDs, and automatic transfer switches, so the event sequence can be reconstructed accurately. During execution, I command each fire mode and manual override. I time the damper stroke, compare the end switch indication with the actual blade position, and verify the VFD override, output, and motor or fan operation. Finally, I correlate the command with downstream power, damper position, and airflow. I deliberately inject mismatch and loss of proof faults, confirm the system responds correctly, and document restoration and retesting. The approved witness script, calibrated instruments, synchronized logs, and explicit abort criteria are what make the result defensible. This is a functional proof of the complete interface, not a checklist of isolated devices. This slide presents an example witness test script for clean agent retention, fire ventilation, and the authorized post-release purge interface. The objective is to prove that the system holds the agent safely, prevents premature ventilation, and allows purge only when the required conditions and authority are in place. Preparation begins with a safe simulated release input. Before execution, I confirm the approved damper, shutdown, and retention logic, and define the atmosphere and authority gates that must be satisfied before purging. During the test, I verify that HVAC equipment stops, the enclosure boundary seals, and the purge command remains unavailable throughout the retention period. Once every gate is met, I apply the authorized clear or purge command. The final step is to prove and record the complete sequence. I check for conflicting smoke control commands, verify warnings and feedback, and confirm manual authority. Then I document the chronology of release, retention, clearance, purge, and reset. The key principle is purge is never allowed to bypass the retention and authorization controls. Approved scripts, calibrated instruments, synchronized logs, and explicit abort criteria make the test safe, repeatable, and auditable. This slide defines the acceptance evidence pack, the final record that connects the approved smoke control design to measured, witnessed, and authorized results. The key principle is traceability. Every acceptance criterion should lead to clear proof in the field. No criterion is complete until its evidence is assembled and its status is understood. The first group covers design and configuration. That includes the approved analysis and zone matrix, control graphics and point schedules, fan and damper information, door and instrumentation drawings, plus any approved changes or deviations. The second group is test and measurement. Signed FAT, SAT, and IST results are supported by differential pressure, airflow, velocity, and door force readings. Calibration certificates, standby power and failure tests, manual control evidence, photographs, and synchronized event logs help demonstrate that the system performs as intended. Finally, operations and closeout confirm that the system can be managed after acceptance. This includes defect and retest records, O&M information, impairment procedures, training, restoration and post-fire purge procedures, and the applicable authority or AHJ sign-off. Together, these records create a defensible handover package, not just a collection of test documents. This module focuses on Section F, Operations, Impairment, and Competency. The central requirement is straightforward but demanding. Throughout the system lifecycle, I need to keep calibrated sensors, available fans and dampers, current response procedures, and competent manual control in place. Readiness is not a one-time inspection. It is an ongoing operating discipline. The slide organizes that discipline into 4 connected actions. First, I inspect the system and verify that critical equipment and controls remain in the expected condition. Then I exercise the system so people and equipment demonstrate that they can perform when needed. If part of the system is impaired, that condition must be recognized and managed rather than overlooked. Finally, I improve by correcting weaknesses and carrying those lessons forward. The broader learning path is operate, trend, inspect, exercise, correct, and demonstrate readiness. That sequence connects daily operation with evidence of performance. In practical terms, the goal is to know not only that the system exists, but that it remains functional, understood, and ready to respond when the situation requires it. This slide focuses on the governance needed to keep smoke control and fire ventilation performing as accepted, long after handover. The system has to remain governed in fire mode, not simply installed and commissioned. That means maintaining set points, pressure sensors, damper travel, fan duty, standby power, and control priorities. The lifecycle rhythm is straightforward. Inspect, exercise, calibrate, drill, and improve. For fans and drives, we exercise both duty and standby equipment, check mechanical condition, and prove the VFD fire mode, feeder, automatic transfer switch, and standby source. For dampers, ducts, and boundaries, we stroke actuators, inspect blades, seals, and end switches, and keep access and discharge paths clear. We also verify fire stopping and door condition. Sensors and controls require calibration, alarm limit checks, priority testing, mismatch alarms, event clocks, and discipline management of software, setpoint, and graphic changes. When an impairment occurs, isolate the exact zone, establish compensatory actions, notify the authority, operations team, and responders, then retest after repairs or building or HVAC changes. This is how accepted performance stays real throughout the system's lifecycle. This workshop asks me to prove a representative fire zone from the initial alarm input all the way through safe restoration. I'll begin by choosing a high-rise data hall, critical room, or basement area, then identify the fire input, adjacent zones, and any protected shafts involved. Next, I'll set the smoke control objective and map the devices needed to achieve it. That means considering pressure relationships, exhaust and makeup air, relief paths, and the required door and damper states. The response and test plan must also define how success will be demonstrated. I'll specify where differential pressure, airflow, velocity, and door force are measured, and I'll identify the manual command and fallback operation that must be witnessed. The key quality gate is simple but demanding. Every command needs physical feedback and a measured result. I also need to confirm that system reset cannot create an uncontrolled smoke path. Finally, I'll review the complete one-page plan for clarity, consequence, and safe restoration, using the relevant fire control terminology consistently. The accepted evidence base is the point where a smoke control design becomes something that can be trusted in operation. The central idea is simple. Calculation alone is not acceptance. Acceptance requires engineered pressure and airflow, exercised under firefighter authority, supported by calibrated field proof, explicit fallback arrangements, and controlled restoration after an event. That evidence has three connected parts. First is the matrix, coordinated control and equipment matrices that show how the system is expected to respond across zones and pressure control functions. Second is the proof, synchronized FAT, SAT, and IST records, supported by calibrated test data rather than assumptions. Third is governance, including clear procedures for operation and maintenance, impairments, drills, and sequential restoration. The most important concept is a verifiable chain of custody from design assumption to physical site reading. That means someone can trace the reasoning all the way to evidence such as a door force gauge reading in the field. When those links are complete, the system is not merely designed. It is demonstrated, governed, and ready to be accepted. This final slide brings together the references and governance that support Module 12A. The approved smoke control analysis, adopted standards, project-specific listings, and AHJ or DAMCR conditions must be used together, with the governing authority and approved fire strategy taking precedence. Key references include Indonesian regulations, applicable SNI provisions, NFPA and IFC or IBC requirements, ASHRA guidance, AMCA standards, and measurement uncertainty principles. Verification also depends on listed equipment, approved cause and effect logic, testing records, calibration, maintenance, change management, and retesting. The goal is safe, documented return to normal.